All right, so just this is for Rose's benefit. So we're going to work on chapter 8 today, just the theory of it, and then we will do sample questions and problems next time. Okay, Tuesday. All right, good. And also I would want to make it clear that there's a test that I should be giving you soon for this this last section, this probability section with the normal and all. So I will let you know soon about that. I think there's 2 quizzes and a test that I owe you. I'm sure you've been wondering about that, you know. This wasn't a good week to give a test anyway, so. All right.
Is there
so,
any homework for this week?
I might give you like maybe 3 problems from chapter 7 or something. It'll be new next Tuesday. So I will definitely do that. Nothing else will be due next Tuesday. Probably I'll give you a couple quizzes to do for next Thursday. Maybe. I think I need to give you 2 more quizzes for the last section we were just in. And also that test. My guess is the test I probably will give you a week. Well, I will post it probably next week. Give you about a week to complete it. All right.
Can you give us more time to finish the test?
Oh, you mean want more time during the test?
Yes.
All right. So I will. Let's see. I gave you an hour and 15. I'll give you an hour and a half. An extra 15.
Thank you.
All right. Yeah, I'm okay with that. So I'll make it a 90-minute test. Same thing, 22 multiple choice questions, all right?
Okay.
Thank you.
Yeah, you're welcome. I don't want you to, get prematurely gray or,
Don't worry, I'm already going gray.
And, I don't want you to look like me, but that's all right. All right, so I will share the PowerPoint with you. All right. So what have we been doing? What were we doing last time? We were talking about the normal distribution, right? The bell-shaped curve. It's a continuous distribution where the probabilities are based off of ranges of values, right? We want to find the probability of a range of values as opposed to an individual value. And we use software to figure out the answers, okay? Now, the important conclusion about what we were doing was that when we were finding these probabilities, we were basically finding the probability of selecting somebody at random from the population, okay? Now, in reality, when we work with statistics, we don't just choose one person and examine that one person, right? We don't choose one person at random and then do an investigation and then write a paper and make a conclusion. No, we do. We have a few people, right? Maybe thousands of people. So we have what's called a sample of people. We randomly sample people. We use, simple random sampling. We use stratified sampling, cluster sampling, whatever we use to get the people that we want. All right. Why do we do random sampling? Because we want to make what's called inference. We want to take the conclusions of our sample and say something about the entire population. And that's what we're going to learn how to do. Now, however, the use of the normal distribution that we're going to be using from this point forward is going to be a little bit different when we actually do inference. And that's because we're not only going to be dealing with one person now, we're dealing with a sample of people. Okay, so what we have to think about now is the fact that when we come up with a sample, it's one of many samples that we could possibly choose, right? We have 1 million people and we want to choose a sample of 1,000 out of the million. There is trillions and trillions and trillions of possible samples, all right? If we use that combination symbol, right, where we're taking a group of people and choosing a certain number and coming up with a number of combinations, it's the same thing with samples. If we have 1 million people and we want to choose 1,000 people out of that, then the combination symbol is 1,000 for for the group, the whole thing, and then we're choosing a group of 1,000 people out of 1,000,000. So it's 1,000,000. Take 1,000 out of it. You can picture how big that number is. It's huge. It's enormous. And that's basically the number of samples that we're choosing from. So what we need is what's called a sampling distribution. That is a list of it's a list of statistics about the samples that we could possibly choose from. In other words, instead of choosing a person from a population, we're choosing a sample of a certain size from all the other possible samples of the same size. You see what I'm saying? Most students, when they hear this, it's hard to grasp that concept. But if you could picture taking a sample and finding the mean. Let's say we want to know the height of 100 people in our sample. All right, or let's say 1,000 people, whatever, 1,000 people in our sample. We want to measure their height, and then we're going to take the average height. We're going to take the mean of those 1,000 heights. All right. Now, my question to you is, do you think that mean, that sample mean that we got, is going to be equal to the population mean of heights? Now, most likely it's not going to be equal to it, right? Because the population has 1,000,000 people, right? And if we could measure all 1,000,000 people, their heights, and take the average, it's probably not going to be the same for that one sample. Suppose you, Steve, take a sample of 1,000, and you've come up with your sample mean. Han, you go out and you do your own sample, random sample. Do you think, number one, do you think your sample and Steve's sample are going to be the same people? Most likely? No, most likely not, right? So do you think the means are going to be the same? The sample mean? No, that's sampling variability. So each sample will be different. Now remember, in most research, we're only going to take one sample, right? We're only going to look at one group. So how can you possibly take the results of that sample, which not only are probably not going to match the population, but not going to match any other samples that are out there? And how can you take the results and say something about the population? Seems kind of impossible, right? A really hard task. Well, this chapter tells you how to do it, right? It's the key for not only the rest of this course, but any other course you take in statistics, undergraduate or graduate or PhD. Without this chapter right here, the rest of statistics would not exist. It just wouldn't exist at all. So it's this whole idea of what's called a sampling distribution. So what is a sampling distribution? Again, if you could list all the possible samples of size, let's say 1,000 people, all right? So when I say size, I'm referring to the number of people in the sample, all right? We use a small letter n to represent the sample size, number of people. So if I say 1,000 people in the sample, I mean, and small n is equal to 1,000. Big N, capital N, it refers to the number of people in the population, if we happen to know that, all right? So it's big N is the population size, all right? So keep that in mind when we start looking at some of these formulas that are coming up. But now we're dealing strictly with samples. Suppose we were able to list all the possible samples of size size 1,000 from that population, from a particular population. Suppose we were able to do that, and we were able to know the sample mean for each one of those zillions and zillions of samples. All right. Could we come up with a distribution of those means from those samples? And the answer is, well, of course we could, right? We have computers now, we could probably list them all. So that's what's called a sampling distribution. A sampling distribution, all right? of sample means. If we're measuring the mean of each sample, it would be of sample means. The sampling distribution of sample means, which means the mean of sample 1, the mean of sample 2, all the way up to the mean of sample whatever the last sample is. Each one will have its own mean, and therefore we could find the mean and standard deviation of that sampling distribution, couldn't we? Because we have all those numbers, and we can find the mean and the standard deviation of all those numbers.
Mm-hmm.
All right, you get the idea what I'm referring to here. And we're going to be using, I'm sorry, yes? Okay.
I said yes.
Yeah. So we're going to be using this idea to be able to do what's called inference. And we're going to learn 2 types of inference well, actually 3 types, actually. We're going to learn how to estimate population parameters like the population mean. We're going to learn how to do that using the sampling distribution. We're going to do hypothesis testing, where we have some hypothesis about the population mean, maybe population mean of something, all right? And we're going to test the hypothesis using sample data. That's what most research is doing. And the other thing is we may be able to make a connection between 2 variables or maybe multiple variables through what's called regression, okay? And that way we could possibly make predictions of maybe we are hypothesizing a causal connection between one variable and another variable. And maybe if we come up with some sort of equation as an estimation of that relationship, then we may be able to make a prediction or predictions. If we know an X, there's our Y, something like that, okay? So all of that is based on sample data, all of it, everything that I just mentioned. And it requires us to make a statement about what's called the sampling distribution, okay? Because again, we're only going to have one sample with one sample mean, all right? Now we're also going to talk about what's called a sample proportion. And what's a sample proportion? Well, if you remember with the binomial, binomial was where we had 2 cases, right? 2 cases. And we're interested in one of them as opposed to the other, right? And we repeat the experiment over and over again. The probability of success remains the same, that sort of thing. And we want to know the number of successes in N trials. Well, we could answer the question in terms of the number of successes, or we can answer it in terms of the sample proportion, which would be the number of successes divided by N, which is the sample size, okay? So we can take a binomial and convert it into a proportion by simply taking the number of successes and dividing by the number of trials, which is N, okay? All right, so let's get to it. And you all can see the screen, right? You can see it okay?
Yeah.
Yeah, okay. All right, so these are the 2 types of distributions that we're going to work with. Sampling distributions of means, if we're taking the mean of each of the samples, and we could also take a proportion, right? We could take a proportion. In other words, maybe we have a research question, right? Who are you going to vote for, Donald Trump or Joe Biden? Hate to remind you of what's going on in the real world, but right? There's a binary choice there, right? And so we are going to look at the possibility of the proportion of people who vote for Trump, the proportion of people who vote for Biden, okay? And it's basically the number of people who vote for that person divided by the total number of people in the sample, okay? And that's the proportion. So we can measure that for each sample also. We could come up with a proportion as opposed to a mean. A mean is what? It's an average of what? A quantitative variable that we can measure, like height, weight, right? Money, whatever it might be. So in this chapter, we're going to talk about the sampling distributions. We're also going to talk about what's called the central limit theorem. I mentioned that to you last time. All right. And it says here we're going to determine the effect on the sampling distribution when the samples are relatively large compared to the population from which they are drawn. Now, normally, samples are very small compared to the populations that we have, okay? If we have it, like I said, out of a population of 1 million, we may take a sample of 1,000 people, right? And that's 1 out of 1,000. It's just 1 out of 1,000 is the size of the sample relative to the size of the population. Typically, if the sample size is less than 5% of the population size, then we don't have to worry about what we're going to talk about. We don't have to worry about making any adjustments to our sampling distribution, right? But if the sample size is large, in other words, it's more than 5% of the population size, then we may have to do a little tinkering, which I'll talk about in a minute. All right. Now, the first thing we want to talk about is the population itself. Now, the population itself could be normally distributed, right? Could be like heights, right? Heights are typically normally distributed. Or it could be skewed. For example, income. Income is not normally distributed. Income is skewed, right? It might be skewed to the right, right? Because of those unusually large incomes that some people have, right? So income is skewed. So some populations are normally distributed, some are not, or not even close to being normally distributed. But we still can talk about the center of each of those distributions. We could still talk about the spread or standard deviation, all right? We can still make those measurements. Now, the normal distribution has those special properties, right? Where we can calculate the probabilities between two values, right? And the normal distribution is used throughout statistics. So we want to use it if we can, as opposed to using a skewed distribution where we may not be so much familiar with how to find probabilities, right? So normal distribution, yes. Skewed distributions, we want to avoid those. So the question is, how can we get around this problem if the population is skewed? Is there some property that we can use that gets around that? Because if it's skewed, we're going to run into some difficulties. And the answer is the sampling distribution, all right? You're going to see that the sampling distribution is going to solve the problem that we're going to have if we have a skewed population distribution. Now, this set of slides here, let me see if they do. No, they go right into the you know what? I think what I'm going to do, instead of because I thought that, yeah, they don't give any good examples here. So what I'm going to do is I'm going to open up the ebook. All right. So just give me a second here. I'm going to open up Cengage. And you can just follow along. You don't have to worry about opening it up yourself unless you really want to. Just give me a second for it to open up. And it'll just take a minute. And what I'm going to do, I want to show you a demonstration of what a sampling distribution is by coming up with an artificially small population. All right. Artificially small meaning like 4 or 5 people in the population. All right. Just to demonstrate what we'll be talking about. Because otherwise, I think, let me see what's in here. Oh, I'm in the wrong Cengage thing here. So sorry about that. So let me try it again. That's not it. I have textbook also with Cengage, which I use for Rowan. There you go. Sometimes I get the two mixed up. All right, so this should open up in a sec. And then, of course, I'll display it to you. You don't see what I'm doing right now. So there we go. All right, so we're in chapter 8. There we go. This is what I want. All right, so let me share this screen with you. All right, so this is actually 8.2 in your textbook. And it's talking about, it's a preview of a sampling distribution. So it's defining what, the population, what a population is. So suppose we have a population of 4 people, all right? And it's a really silly example. And each person has a certain number of bottles of Diet Pepsi in his or her refrigerator. So remember, this textbook's kind of old, like 9 years ago. So maybe 9 years ago, people drank. I don't know if people still drink Diet Pepsi. So Bill had, you do. So Bill has 1 bottle of, bottle of Diet Pepsi. Carl has 1. Denise has 3, and Ed has 5 bottles of Diet Pepsi. So X is the random variable, the number of bottles of Diet Pepsi in your refrigerator. All right. So there we go. Now, if we wanted to find the average number of bottles of Diet Pepsi, we would literally, now this is a population, by the way, of 4 people. We would literally just add up these 4 numbers here and divide by 4. And we get 2.5. 2.5 is your mean. That's mean. All right. We can also find the standard deviation. Well, so what would we do? We would take that mean and subtract it from each of these values and then square it and divide by 4. Now we're dividing by 4, by the way, because it's a population. We don't divide by n-1. We divide by 4. And then we take the square root of that number and we get the population standard deviation. All right, we can do that. Easy to do with just 4 numbers. Now, what if we decide to do the following? What if we decide to take a sample of size 2 from this population of 4 people? So using the combination symbol, that's 4, take 2. All right, 4 in the top, 2 in the bottom. And if you run, do the factorials and all of that, you end up with how many possible samples of size 2?
6.
6, right? Is it 6?
Wait.
Or yeah, it's 6, isn't it? 4 given 2.
Yeah.
Yeah, 4 times 3 is 12.
Yeah.
Divided by 2 is 6. So it should be 6 samples of size 2. So we can actually list the sampling distribution. And so that's what we're going to do. We're going to list those 6 pairings. There they are. Bill and Carl, Bill and Denise, Bill and Ed, Carl and Denise, Carl and Ed, Denise and Ed. Now, the order doesn't matter, right? So that's why we can do combinations here. And what are we doing in this case here? What do we calculate? The sample mean, right? The sample mean. Well, Bill and Carl each have 1 bottle in the refrigerator. So the average is 1, obviously. All right. Does that make sense? We're just taking the sample, a mean of sample of size 2. You can't get any easier than that. I think either I'm frozen or you're frozen. I'll continue talking anyway. All right. You can hear me, all right?
Yes.
Yeah, I can hear you.
All right. So we just have 2 values. When we have 2 people, we have the number of bottles of Pepsi in for Bill and the number of bottles of Pepsi for Carl. In this case, it's 1 each. So the average is 1. Bill and Denise, well, Bill has 1, but Denise has 3 bottles. So the average is 2. So you can see we're just averaging those values, right? That's all we're doing. Easy. Now we come up with how many means? 6 means for each of these samples. So if we were going to actually choose a sample size 2, we'd just choose one of these 6, wouldn't we? We wouldn't do all 6. We'd just choose one of these samples of size 6. But we're able, in this case, because the population is so small, that we can list all the samples of size 2. And we can calculate the sample mean, which is the mean number of bottles in their refrigerators, all right? Just for those 2 people, each of those 2. And we come up with this list here of 6 means. Now remember, the original population had 4, right? And we simply, to find the mean of the population, we just added up the 4 numbers and divided by 4. And we got 2.5 as the mean. Here, we end up with 6 means. And here's the deal. If we took the average of these 6 means, you do it right now with your calculator, guess what we'll end up with as the mean?
2.5.
2.5. And that's mathematically certain. It's a mathematical certainty that the mean of the sample mean is equal to the mean of the population. Isn't that a remarkable result?
Yeah.
That you can actually equate those 2. Okay? So typically in research, we don't know the population mean, but we could certainly come up with some idea of what the sampling distribution mean is by saying it's equal to the population mean, all right? We can make that statement. Do it with any of these cases here. Now, if we add these up, there's 6 of them, right? We have 7, 9, 12, 14, 15 is the sum of these 6 numbers, divided by 6 is 2.5. All right? So the sampling distribution mean is equal to the mean of the population in all cases. You know, you could try other possibilities, different populations, and you'll see it's true. And you can prove it mathematically without going through these individual cases. All right, so there's one result. The sampling distribution's mean is equal to the population mean. Now, what if we took the standard deviation of these 6 numbers? Remember, we could take the standard deviation of those 4, right? Of those 4. Now, in this case here, the first thing we would have to calculate is the variance, right? We'd have to calculate the variance. Now tell me, when we calculate the variance, we have the mean. What are we going to use in our denominator? We're going to use 6 or 5? What do you think?
5.
It says 5.
I say
Steve?
6.
You'll say 6. And the answer is 6, because this is a population. It's like a population. It's the list of all possible samples of size 2 from a population of 4. All right?
Okay.
And therefore, this is a complete set. It's not a subset. Remember, a sample is a subset. This is a complete set of samples. Therefore, the variance and likewise the standard deviation, you can look at it as if it's a population. You calculate the variance as if it's a population. Now, when you do this, what you're going to find is in almost all cases, I would say in all cases, the variance and likewise the standard deviation of the sampling distribution of sample means is going to be less than the standard deviation of the population. It'll be less than. So that's one thing that I'll just say. It's always true. Always true. If you have a sample of at least 2. All right. If you have a sample of 1, you know, it's not really a sample. Okay. So that has to be true. Now, if we now take, now that I've demonstrated how this sampling distribution thing works, right? You take the list of all possible samples, you find your sample means or proportions, depending on what you're measuring, right? And then you find the mean and standard deviation in the normal way, as if it was a population. And you would notice the mean is the same as the population mean. the standard deviation of the sampling distribution is less than the standard deviation of the population. But what if you exponentially grow the population, make it infinite, theoretically infinite, huge, right? Almost as if it's infinite. What ends up happening is that the standard deviation of the sampling distribution starts to approach a certain value, okay? Comes to up to a certain value. And what that value is, and I'm going to now go to the PowerPoints. All right, so let's go back to the PowerPoint here. It's going to approach this formula down here. Let me explain the formula. Sigma, of course, is the standard deviation of a that's our population standard deviation, right? That's what we use, the Greek symbol sigma. But it has an X bar next to it. What does X bar represent? The sample mean. This symbol here, sigma X bar, is what's called the standard deviation of the distribution of sample means. In other words, the standard deviation of the sampling distribution. Another name for it, and the one that's used all the time, is the standard error of the estimate. The standard error of the estimate. And it's equal to, if you have an infinite population, it's equal to the standard deviation of the population divided by the square root of the sample size. That's a remarkable result. As the population gets infinitely large, then the standard deviation of the sampling distribution is not only smaller than the standard deviation of the population, but it's smaller by a factor of 1 divided by the square root of the sample size. What's required here is that the sample size of the size of the sample has to be less than 5% the size of the population for this formula to work. Okay, for the formula to work, but it's a very good approximation. So what we've just come up with is the following. We've come up with the idea that the sampling distribution of sample means, the mean of the sampling distribution is equal to the population mean, and the standard deviation of those sample means is equal to the standard deviation of the population divided by the square root of the sample size. Now, what this means is, number one, the larger the sample, the smaller the standard deviation of the sampling distribution. And that's because the numerator is fixed, but the denominator is becoming larger. And whenever we have a fraction and the numerator is fixed and the denominator is growing, then the fraction is getting smaller. That's a remarkable result also. And the reason why it's useful is because whenever we want to make an estimate of a parameter using sample statistics, we want the result to have as small a variability in the sampling distribution as possible. Think about it. We have all these possible sample means, right? If the standard deviation of those sample means is small, then they will all be close to each other in value. And therefore, we can say for sure that we have a legitimate calculation of the distribution of the sample means, because the mean is in the middle, hopefully. We'll talk about that in a minute. And then we have a small standard deviation. So it doesn't matter which sample we end up with. They're all going to have sample means close to each other. And when we're using the sample means to estimate the population mean, it doesn't matter which one we have, theoretically, because if we have a large enough sample size, our standard deviation of these sample means will be small, right? Relative to the mean of the sampling distribution. And therefore, so they're all going to be, congregating around the same value. And then we could just choose one. It doesn't matter which one we get. All right. And we don't have to worry about the sampling variability so much. So sample size is critical. All right. And I'm showing you why. If the variability is too much between different sample means, possible sample means, then it does matter which one you get, right? Maybe one of them is close to the population mean, and another one is way far away from the population mean, right? And we don't even we won't even know which one is close and which one isn't. So we want to make sure that our sampling distribution has a small standard deviation. All right. So you see theoretically what I'm coming up with. Now, here's the next question. All right, I have a mean of the sampling distribution. Theoretically, I don't know what it is. The only thing I have is the mean of the sample that I chose, right? But theoretically, there's some sampling distribution. And what do I know? I know that the mean of all the sample means is going to be the population mean, right? I know that. So that's number one. Number two, I know I can control the spread of the sampling distribution by increasing the sample size. But what that also does, if the spread is less, that means the means are all close to each other, right? They're all close to each other. And if the mean of the sample means is equal to the mean of the population, then our sample that we have, the mean that we have for a sample, is got to be pretty close to this population mean. You see what I'm saying? If the mean of the sampling distribution means is equal to the mean of the population, and if the standard error here is small, that means these sample means are near each other. The average of those is going to be right in that little cluster of sample means, and that's going to be equal to the mean of the population. See what I'm saying? And therefore, if our particular mean is probably going to be pretty close to what? The mean of the population. And that's why this stuff works. If you can understand that concept, if you can picture it in your mind, then you can understand how you can estimate population parameter by using a sample statistic. Because you're controlling what you can control here. And the only thing you control is the sample size. Because the data is the data, right? I mean, whatever it is, I mean, you can't control how tall people are or what they weigh or whatever, all right? The income, right? Whatever those things are, you're not controlling those. You're just measuring those or coming up with answers to questions like, who do you like, Trump or Biden? But I hope you can understand how this works. The smaller the standard error, this sigma x bar, the closer all these samples are to each other. And because their mean is the population mean, that means the population mean is in that cluster also. Okay? And that's the key. And what we want, now obviously, there's going to be some outliers in the sample means. What we want is a high percent of the sample means to be in that middle cluster near the population mean. And we don't worry so much about what? The possibility of these outliers that are away from the population mean. We can't control those.
Mhm.
So we might want to limit the percentage of those. And there's a way of doing that. There's a way of doing that. So that's what this whole process is going to be about. We're going to try to create a cluster of maybe 90 or 95% of the sample means to be close to each other. We know the population mean is going to be somewhere around there. And then there's going to be a few, maybe 5 or 10, hopefully 5%, let's say 5% of the means that are going to be away from the population mean. Okay? They're going to be away. I don't mind the odds of having 95% of the possible samples be close to the population mean and 5% not. I'm willing to go with that gamble. You can't guarantee all 100% are going to be close to the sample mean. So that is this theory behind this whole, I mean, without going through any math, literally, except for this little bit of math, that's the theory behind inference, is that we want to create a cluster and then pick a sample out of that cluster and have maybe a 95%, be 95% confident that that sample that we picked has a mean that's close to the mean of the population. All right? And that is going to be the basis of what we're going to talk about in chapter 9. But I have to say it now because this is the reason why we want the sampling distribution. Otherwise, it's a complete guess. Without this idea of sampling distribution, we have no idea whether the sample we have is any good. We don't know if it's close to the population mean. We don't know if it's far away from the population mean. We don't know if it's a good estimate or not. We just don't know. But with this theory here of the sampling distribution, we can actually come up with a theoretical basis for estimating the population mean from one sample, from the data from one sample. Knowing that that sample, we're 95% confident that sample is in that cluster, right around the population mean. All right, that's the theory behind this. Any questions about that? Because that is, both of you guys I know can understand this concept. I teach this, by the way, to people, some people in Camden County who have trouble just using their calculator, right? They have difficulty with mathematical concepts. This is almost impossible for them to get. It's really hard. I don't think it's appropriate for most people to be learning this unless they are going into research or something, you know, because in real life, people aren't going to be using this in business and all. They're going to be just, you know, creating data and then analyzing it a little bit and then presenting it to people. That's what they do. This is a very difficult concept for an introductory student to get initially. So if you got it, if you sort of get what I'm talking about, I think you'll understand the rest of the course. But both of you, I think, have good backgrounds in math, right? And I think you can conceive of what I'm talking about. All right. Now, what do we do? Now, here's the deal. And they did this without going into much detail here. And I'm going to make a point. If you have your sample of sample means, and if you, if again, the bigger the sample size, the more the smaller the standard deviation is, the standard error is. But there's another thing that's happening also. And this is really cool. Even if your population is skewed, let's say we're measuring incomes of people, right? And we know it's skewed right. Even if the population is skewed, population distribution of values, the sampling distribution always becomes approximately normal as the sample size gets bigger. And typically people use the number 30 as the minimum sample size for the sampling distribution, with its mean and with its standard deviation, which is standard error, right? You can picture it becoming normal. It will become normal. That's the amazing thing about it. As the sample size gets big, the sampling distribution begins to look like the normal, even if the population distribution is not normal. Isn't that amazing? Now, if the population is normal, the sampling distribution is automatically normal. That's mathematically certain. Now, there's a way of showing that, but that would require you to have taken a course in mathematical statistics, which requires calculus and all that, this is not that kind of course. So there is a mathematical way of showing that with the normal distribution. You can have a linear combination of normals and it creates a normal, okay? You don't need to know that, what I just said. But the important point is, if the population is normal, the sampling distribution is going to be normal automatically. Doesn't matter the size of the sample. It could be sample size 2, doesn't matter. But if the population is non-normal, like skewed right or skewed left, severely maybe, like with income, then there's a minimum sample that's required for the sampling distribution to begin to look like a normal distribution. And why do we want it to look like a normal distribution? Because we can calculate probabilities easily, the same way we calculated in chapter 7. Now, here is the big deal. Remember, the standard normal has a mean of 0 and standard deviation of 1, correct? And if the sampling distribution with a large enough sample size is approximately normal, it will also have a mean and standard deviation too. The standard error becomes a standard deviation, okay? We can convert it to a z-score by using that formula, right? We'd subtract the mean and divide by the standard deviation. But if we're dealing with a sampling distribution, the numerator of the z is, of course, the sample mean minus mu. What is the sample mean? It's the sample mean of what? The one sample that you have. All right?
Mm-hmm.
What is mu? That is the mean of the sampling distribution, but it's also the mean of the population because they're equal to each other. So that's why they just put mu here. That's important later on to have that in there. So mu is the population mean because it's equal to the mean of the sampling distribution, mu x bar. So they're putting mu in here instead of mu x bar. Now, what's the denominator? Sigma x bar. It's the standard deviation of the sampling distribution, which is sigma divided by the square root of n. So this fraction here is in the denominator of this z-score formula. You could put parentheses around here if you want. X bar, the sample mean, minus the population mean, divided by the ratio of the population standard deviation divided by the square root of n. So if I give you a problem and I say, and I tell you this population has a mean of 150 and a standard deviation of 30, and you are pulling out a sample of size 100, and then your sample mean is 170, right? Your particular sample has a mean of 170. You would say 170 minus 150 in the numerator, and the denominator, I believe I said 30. 30 is your standard deviation of the population divided by what? The square root of 100, because that's your sample size. And of course, the standard error in this case would be 1/10 of the population standard deviation, wouldn't it? Because the square root of 100 is 10. And so 30 divided by 10 is 3. So your denominator would actually be 3 here. 30 divided by the square root of 100 is 3. So your Z actually becomes what? Bigger as a result of this. Which means it's what? Further away from the mean. Further away from the mean. So that's going to be an important concept to understand later also. So if you were going to, in this case, use the normal distribution to come up with a probability, right, between two values, you can convert it to a Z with this formula and then use the standard normal table or standard normal with your Excel, whatever it might be, or you would use a mean of what? 130, 150, right? And you would use a standard deviation of 3. Not 30, 3, because it's a sample of size 100. And this formula here is converting a sampling distribution value into what? A Z-score. Good. I hope you both, I'm glad I'm seeing nods there, because again, when I present this, typically I get people staring at me like I might as well be talking in a foreign language. But I'm glad that you're getting it. Good. Now here's the central limit theorem. This is the theorem that's responsible for saying that the sampling distribution becomes normal. It says here that the central limit theorem, this is a mathematical statement, but we're not seeing the math. It says the following: the larger the sample size, the more normal the distribution of sample means becomes. In other words, the sampling distribution begins to look normal. All right? It's central to the concept of statistical inference because it permits us to draw conclusions about the population based strictly on sample data without having knowledge about the distribution of the underlying population. How about that? You don't even need to know the distribution of the underlying population. This theory says if the sample size is large enough, the distribution of sample means is going to be normal, period. And we don't need to know anything about the population. It's remarkable. This is the key to doing inference, which is the key to doing any advanced statistics, anything that's more advanced than what we'll be doing in this course. Without this one slide here, without this knowledge, as I said, the rest of statistics wouldn't exist. We wouldn't be able to make any inference. So the normal distribution is key. It's a key thing. We want normality. And if a population is not normal, well, if the sample size is large enough, the sampling distribution will be normal. And then we can come up with probabilities of different things that we'll be talking about. So, and you'll see exactly what we'll be doing using probabilities. What we're using though is the normal curve for the sampling distribution, not for the population. Okay, that's the key. So I'm going to reiterate this again. How are we doing with time? So we're almost we'll be over in about 5 minutes or so. When the population is not normally distributed, the central limit theorem says we have to, well, if we're dealing with sample means, we want the sample size to be at least 30. That's in general. I would say depends on your field of study, how large your sample size should be. All right. So your particular field of research, the researchers kind of know what the minimum sample size should be. If the population is normal, it doesn't matter. There's no minimum sample size. But if we don't know anything about the population, or we do know that it's not normally distributed, then we want a minimum sample size, typically at least 30. That's for sample means, if we're estimating sample means. All right. The center of the distribution is going to be equal to the center of the population mean. That's the key. Without knowing that, without having that knowledge, okay, without having this knowledge that the mean of the distribution of sample means is equal to the mean of the population, and without knowing that we have a normal distribution for the sampling distribution, without that, we can't do anything. You know, our hands are tied. So the center of this normal distribution is going to be what? The mean of the sampling distribution, but it's also going to be the mean of the population. They're equal to each other. Isn't that remarkable? So when we draw our normal curve, we can just say mu for the population, what's in the middle, because it's equal to the mean of the it's equal to the mean of the sampling distribution. Now, what's going to be the standard deviation? When we say the number of standard deviations from the mean, that's going to be the standard error. This is going to be what we're going to use, sigma x bar, which is sigma, the population standard deviation, divided by the square root of n. That's going to be our standard deviation for the sampling distribution. And we just conveniently call it the standard error. All right. This is what we're going to use for the standard deviation. All right, so let's look at a couple of examples and then we'll call it a day. And then next time we'll do more detailed examples from the book. So it says when a production machine is properly calibrated, it requires an average of 25 seconds per unit produced with a standard deviation of 3 seconds. Now, this first sentence is referring to the population of machines. It doesn't mention anything about a sample. So if you're given information in this way, when it says standard deviation, it's referring to the population standard deviation. When it says average, it's referring to the population average. All right. For a simple random sample of 36 units, all right, we have a sample of size 36. The sample mean is found to be 26.2 seconds per unit. What z-score corresponds to this sample mean? And remember, this sample of size 36 is one of many samples of size 36 that measures what, right? It's measuring what? The amount of time to produce this, whatever it's being produced, all right? So this is one of those samples, and we want to find its z-score. Well, what is the mean? What z-score are we going to calculate? We're going to calculate it for what? For the sampling, from the sampling distribution. Because this mean, right, of 26.2 seconds is not for one unit. Right? It's not for one unit, it's for 36 units. It's the mean of 36 units. It's not one unit's value for time. It's the average of 36 units time. So if it's the average that we're looking at, we must use the distribution of averages. The mean is the standard deviation of the distribution of averages. Because this is one of how many averages? You know, millions of them, whatever. So it's going to be x bar minus mu x bar. But remember, mu x bar is equal to the population mean, which is 25. You can automatically just put 25 in there. The denominator is going to be the standard deviation of x bar, but that's equal to the standard deviation of the population, which is 3, divided by the square root of what? The square root of the sample size, which is 36. Now in this case here, 3 divided by 30 square root of 36 is 3 divided by 6. So that's a half, right? 0.5. But I know from my mathematical training that if you divide by a half, it's the same as multiplying by 2. So the numerator is 1.2 times 2 is 2.4, right? But anyway, I always tell my students, when you use your calculator, put parentheses around the numerator and then put parentheses around your denominator when you divide. And you end up with 2.4, and that's your z-score. Now you have a standard normal score. Now, standard normal, by the way, it's unitless. It doesn't have units. All right, there's no units reference to that. It's not dealing with seconds. It's just dealing with what? Because then, when you use a z-score, the numerator has units in it, right? The seconds, the numerator's in seconds, the denominator's in seconds, and the seconds cross out. And so a z-score doesn't have any units. So it doesn't even matter. Once we convert it to a z, we can just use our normal probability tables, if you want to use a table, or use whatever we use, Excel, calculator, whatever. And it just becomes a normal, quote unquote, normal distribution probability question. All right. If we want to know, for example, what's the probability of scoring less than, not scoring, what's the probability if we selected a machine, a sample of machines at random? What's the probability that the sample machines were less than 26.2 seconds? Then we could convert it to a z, but with this formula here, and then use the regular way we've been calculating the normal probabilities. We'll get to that next time. Here, they're actually doing the example here. It's not exactly the same question. They're saying, what's the probability that the mean for a simple random sample of this size will be at least 26.2 seconds? Now, in this case, they're saying, all right, I'm going to select a sample of size 36 at random from where? From the sampling distribution of sample means. I'm pulling one of these samples out. What's the probability that its mean is at least 26.2 seconds? So in this case, notice it's saying probability that X bar is greater than or equal to 26.2 seconds, not X. X would be what? An individual machine, right? Here, we're saying 36 machines. Okay, so now we want to know, I'm pulling a sample of size 36 out. What's the probability that the sample mean is at least 26.2 seconds? And therefore, since we're pulling it out from the sampling distribution, we have to use the sampling distribution, the mean and standard deviation of the sampling distribution, to answer this question. Now they use, of course, what? They converted the 26.2 into the z and then answered the question. But you don't have to do that. As long as, like in Excel, you can put in a mean of what? 25, but you better put in that the standard deviation is 3 divided by the square root of 36. That's the standard deviation. Because it's from the sampling distribution, not from the population. And finally, I just spent a couple more minutes on this. What if we were dealing not with a mean, but with a proportion? In other words, we're counting the number of successes. And so a good example is, again, a survey, right? And the survey has two possible, I have a question, is two possible answers. And we want to know the proportion of all the people taking the survey that said, I voted for Joe Biden, okay? Or I'm going to vote for Joe Biden. Not that I voted for it. I'm going, it's a poll, all right? So what do we end up with? A sample proportion. Now, in the book, the sample proportion symbol is P. Almost every other book I've used, they use P with a hat above it. And the hat that I'm talking about is above the number 6 on your keyboard. It's the caret symbol, all right? Little hat. So P hat, most books use as the sample proportion, and they use P without the hat as the population proportion, okay? But that's not what they're doing here. In this book, they're using P without the hat. They don't even use hats in this book. They use P as the sample proportion, and they use pi as the population proportion. Now, if you're all right with that, if you know that pi doesn't mean 3.14, if you know it's a symbol for the population proportion, I'm okay with using it for the course. Are you both okay with that?
I think so.
All right. So again, with some beginning students, they get confused. They look at pi and they think they're dealing with pi, 3.14. So that's why many books don't use it, because a lot of students get confused. But if you know that it's a symbol for the population proportion, then we'll use it. Now, here's the deal. With the sample mean, the central limit theorem says you need typically at least 30 as your sample size if your population is not normal, all right? What do we use to determine normality when we're dealing with a population proportion? Now, proportion is not continuous. It's not a continuous random variable, right? It's not continuous. Now, there is a section in chapter 7 which talks about using the normal as an approximation for the binomial. And we may want to spend a couple minutes with this maybe next time. But my point here is it's different with the proportion, sampling distribution of proportions. What we have to do is we have to take our sample size and multiply it by pi, the population proportion. Now, if we don't have it, which we won't, because typically we're estimating it in our research, then we just simply use p, the sample proportion. And what we do is we multiply n times pi or p, whatever we have that's given. And then we also multiply n times 1 minus pi. Now, 1 minus pi is 1 minus the population proportion. Remember, a proportion is between 0 and 1, just like a probability is. Okay? When we multiply these two, come up with these two multiplications, if they are both greater than or equal to 5, then the distribution, the sampling distribution of proportions is approximately normal. Okay? Now, why do we do that? It's because the pi, or the population proportion, could be very small. It could be very small. It could be 0.005 or something like that. So we want to make sure that n is large enough to compensate for that small probability. So instead of saying n is at least 30, we say n times pi and n times 1 minus pi both have to be greater than or equal to 5. And if that's true, then the sampling distribution is approximately normal. And that's how we determine it. All right? And once again, if the problem doesn't give us pi, it gives us p, we use p instead. Now, here's the other thing. If you listed all the sample proportions of size 2, maybe out of a population of 4, if we ended up doing something like that in our beginning demonstration, we would have found that the mean of the sampling distribution of proportions is equal to the population proportion. Let me say it again. The mean, in other words, if we took the sample proportions for each sample of size 2, all right? And then we took the mean of it. How did we take the mean? We simply add up those numbers and divide by whatever, like we usually do. The mean of the sampling distribution of proportions is equal to the population proportion. It's like the mean of the sample means is equal to the mean of the population. The mean of the sample proportions is equal to the population proportion. So the center of the distribution of a sampling distribution, all right, mu, we would call it mu pi, all right, is equal to pi, the actual population proportion. And here is the formula for the standard deviation of the sampling distribution of proportions. It's equal to the square root of pi times 1 minus pi divided by n, all under the square root. Once again, The larger the sample size, the smaller the square root is. Because the numerator is fixed. But this is the formula that we use for proportions, for standard deviation. We use the same symbol, sigma, but we put a p next to it here. Okay. And why would we put a p? Because it's the standard deviation of the sampling distribution of sample proportions. We'll do some examples of this next time. And then, of course, if we want to calculate our standardized value, we use the same formula, the same z. We would use the sample proportion minus pi population proportion, which is what the sampling distribution mean of proportions, which is the population proportion, divided by what? The square root of pi times 1 minus pi divided by n, which is our standard error. This is the formula for the z-score when we're dealing with proportions. Okay? Don't worry about it yet. We're not doing problems yet. I'm just introducing this to you. And then here's an example right here. We'll just go through it. Let me see if there's, yeah. This correction factor, by the way, we'll do next time. I'm not doing it now. And this is an example. It says the campaign manager for a political candidate claims that 55% of registered voters favor the candidate over her strongest opponent. This is a claim. This is a population claim. This is pi. Assuming that this claim is true, what's the probability that in a simple random sample of 300 voters, at least 60% would favor the candidate over her strongest opponent? Well, at least the 60% represents what? The sample proportion, right? That is, if you pick a sample of size 300 at random, okay, what's the probability at least 60% would favor the candidate? Well, we're going to use the sample proportion as 60.6. So the sample proportion is 0.6. The proposed or claimed population proportion is 0.55. And the denominator, notice we use 0.55 in the formula and not 0.6. We use, if we're given the population proportion or the claimed one, in this case here, we plug that in, and then the sample size is 300, and we end up with a 1.74 as our z-score. So here is the probability. It looks confusing, right? Because there's a p and a p here. The probability that a sample proportion of size 300 is at least 0.6 is equal to the probability that z is greater than or equal to 1.74, and that's 0.0409. So the answer is about a 4% chance in this case that the at least 60% would favor the candidate over her strongest opponent. Don't worry, this looks complicated at first. It isn't. You'll be able to. We'll do more examples of this next time. All right? Don't stress about it. Relax. Once you see more examples, you'll start saying, oh, yeah, I see what's going on. All right? Everybody strains when they first look at this. I remember I remember reading about a very famous PhD in statistics who said when he first learned this stuff, his head was spinning. And he got his PhD from MIT. All right. So if your head's spinning a little bit, don't worry. Everybody's head spins. Right? Just like Michael Keaton in Beetlejuice. All right. So that's it for today. I don't want to go into anything more. That's enough. Because it does, you know, your brain might be a little taxed right now, especially since it's 8 o'clock at night. So relax, enjoy something nice on television like the election. Enjoy the stress-free claims of the various candidates. And anyway, I'm going to shut off the recording. And this is, you can listen to this again if you like.